So today we are going to talk about privilege escalation, kind of vulnerabilities that we are able to exploit in a colorful way because they're affected because of the colors of your keyboard, your mouse, and your lovely mug holder. So we hope it will be an interesting and a funny talk. And let's begin. This is a disclaimer. You don't need to know anything about it. And let's introduce ourselves. I'm Eran Shimony, security researcher at CyberArk, primarily focusing on the discovery and exploitation of local privilege escalation bugs. Besides that, I really enjoy drinking and mixing cocktails and practicing meditation.
Hello, everyone. My name is Lossos, and I'm a vulnerability researcher at CyberArk Labs, focusing mainly on operating system internals. And besides playing with kernels, I really practice and enjoy CrossFit.
Awesome. So let's see what we have on our menu today. We start with the different ways of the methodology we practice towards open source research vs closed source. After that, we will examine the operating system of choice. In our case, is the Linux kernel. So we will know and understand enough for you to understand the bugs, but not too much for you to run to the exit. Next, we will examine a key component that is very important in any kind of privilege escalation talk, is that how can I communicate and interact between the low privilege to the higher privilege? Because every bug usually consists of missed kind of communication or not reacting to the input in a sufficient way. After that, we will see how the change in the colors of the keyboards can cause two bugs. And lastly, we will examine a newly added mitigation into the Linux kernel that greatly reduces the severity of buffer overflow bugs from potential privilege escalation to a mere denial of service. So first part. On the right, we have a beautiful animal, a penguin symbolizing a particular operating system. You can probably guess. And on the left, we have the not-so-elegant and broken window specifying a different operating system. I'll let you do the homework and understand which is one, and we'll start with that. On closed source, of course, we don't have the source code. So in order to really understand what happens under the hood, we need to do reverse engineering. Usually, we do it through Ghidra, either Pro, Radar, Binary Ninja, whatever you prefer. Because of that, because we need to practice reverse engineering, the amount of knowledge we need to have on low level and operating system is quite high, which means that there is a higher barrier to entry for new researchers and developers alike. But the good thing about that is we are able to find bugs in those areas. Usually the companies that practice closed source methodology actually pay a nice bug bounty upon it. And the way we conduct our research is first we do the recon stage, which is critical in closed source more than in open source, because we cannot really understand easily what happens. So the first thing, we try to find as much information as possible on our target. This is usually done by reading blogs, seeing also conference talks like that, talking to people and harassing them on Twitter. Anything goes to save our some precious time. After that, we try to find code leaks. Some people can argue that Windows is almost an open source operating system because of all the recent code leaks it had. Like around 10 different code leaks for every version of the operating system. And the reason it's so important to us is that usually things boil down that we do a decompile of the code that we receive of the current operating system, for instance, and we compare it to a version that like it's traced 2 years ago. And doing a diff between the current version and a version that happened 2 years ago, it's a lot more easier than just looking at the current decompiled output. After that, it's very important for us to closely define our target. If you're practicing vulnerability research in the past, you know that sometimes things can become really hairy and hectic very fast. For instance, if we examine the Win32k-sys driver on Windows, it consists of several thousand functions. And once you start with one function, it can get carried away to a dozen functions and then to a few hundred functions. And that's a no-go, and it takes too much time. So it's very important to us a clear eyesight and know the target. And of course, we mostly need to practice reverse engineering as well. And sometimes we also incorporate fuzzing. But more about fuzzing soon. And on open source, of course, we have the code, which means that we can understand everything that happens under the hood pretty easily, as long as we can read C, C++, and nowadays, when Rust is in the Linux kernel, also that, then we can understand what happened. Besides that, we have the option and the ability to incorporate static analysis tools that very greatly help us to find low-hanging fruit bugs and help us in cases of following between data flows between one function into another. And lastly, we can compile and build the code, which means that debugging, adding instrumentation snippets, it's very beneficial, and it's a thing that we can do a lot easier than trying to hook in or doing shenanigans on closed source. So the way we approach it in this case is first we find the code, GitHub, GitLab, or if you use the dark technologies of something called SVN, be my guest, it also works. After that, we usually use some kind of static analysis tools that they are very good in finding memory corruption type of bugs, usually null pointer dereference, buffer overflow, underflow, and also all the kind of integer overflow type of bugs, arithmetic errors, and so on. If you have more time, we will use something like a CodeQL or more developed static analysis tools that allow us to use kind of a query language to trace the data from one model into another. And to be more contemporary, we can also use something like GPT models or lemmas to actually try to find code. We can upload all the code of a particular project to the AI, and we can ask it to find for a particular case of code. And sometimes it works and it's able to find bugs. The next step, of course, is to compile and to build the software. Usually, we add some debugging snippets that allow us in the following phase that we want to trace the input originating from the user to the target software. And of course, one of the good things about finding bugs in open source research is that people tend to be lazy, and they copy code around a lot in those cases of open source code. So if we manage to find an error in one case, there is a pretty good chance that it will be carried away to another project, and we will see it soon. And also, let's talk about the fuzzy question. To fuzz or not to fuzz? The question of all. For those who are not familiar, fuzzing consists of generating some kind of input against a target function. And in many cases, the fuzzer has some knowledge about the target function, so it's able to generate a payload a lot more in a clever way. Nowadays, you have also the usage of AI to fit the data better. And the good thing about fuzzing is that we're able to cover much ground in a short period of time and testing many different permutations of the payload. The main caveat at fuzzing, if you have done it in the past, that it takes time. If you used AFL, LeafFuzzer, KFL, syscaller, or whatnot, you know it takes time to customize the fuzzer to your own specific solution. So if you're a bit short on time and you don't have a month, then it's usually not the best case of thing to do. A kind of in-between approach is something called dumb fuzzer, and I'm not sure why we have a bird above the dumb fuzzer. Completely coincidence in my case. So a dumb fuzzer means like it's a kind of a in-between approach. So you have some knowledge on the target function. For instance, you have like one function in the kernel that you understand what are the parameters it's supposed to receive, and you just try to generate some input rotation over all the possible parameters. And that's also the approach we did here. And although it sounds a bit foolish, it's quite effective. And of course, if you have more time on your hand, be my guest, use a full-blown fuzzer. And usually, it proves to be very effective, but you need also to have some knowledge about how to build and how to use a fuzzer. And if we want to sum up the advantages of conducting a research on open source, is that first we have endless examples that we can learn from, which means that we don't need constantly to reverse engineer and to look into the bits and bytes of the smaller things. Besides that, there are more low-hanging fruit type of bugs there because people are less focused on open source research, although it has more advantages in some cases that the effects are wider. One of the reasons is that the companies that employ this type of thing pay less bug bounty. Also, we can add it a code, which means it's easier to debug the code eventually. Also, fuzzing is a lot easier because we have the symbols. So we don't really need to decipher and understand what are all the arguments of a target function. And of course, reverse engineering is a lot easier, and mostly it's not needed. The only case it's needed is if the compiler added some kind of mitigation that we will see shortly. And with that, let's talk about the elephant in the room.
Yeah, so the elephant in the room is the Linux kernel, or more specifically, Linux kernel modules. But in order to understand what Linux kernel modules are, let's first understand the general architecture of the Linux operating system. So as you might know, most of the operating systems are divided into two mainly parts, the user space and the kernel space. One of the main differences between them is that the kernel space is the actual privileged part of the operating system that can interact with the hardware. An example of that could be when the user, for example, requests to read a file stored on an external device, which then the request proceeds to go through the kernel, which eventually the kernel will return the data back to the user. When installing an operating system, you will most likely have the kernel shipped with it. So for example, if you will install Ubuntu, you will have the Linux kernel installed with it. But it doesn't mean that the kernel functionality can't be extended in runtime. Extending kernel functionality in runtime is done indeed via kernel modules. But why you will even like to do so? Most of the time, when you're installing a new hardware device, for example, a new keyboard device, just a generic USB device, you will need to install a corresponding kernel driver or a Linux kernel module with it, that it will know how to interact with the hardware. All right, so now that we understood a bit the general architecture of the Linux operating system, let's jump back to our project. So we've conducted a research focusing on the Linux kernel because essentially each bug and every bug in the kernel is critical due to the fact that the kernel is always privileged. And one of the best places to hunt for kernel bugs is in third-party kernel modules, because most of the time they're less examined and they're accessible by restricted users. Exploiting kernel module bugs can have the same impact as exploiting the kernel itself. So from a generic denial of service attack or to owning the entire system via a local privilege escalation attack, for example. The way we've done it is by looking for big vendors that has kernel drivers and examining the code, which one of them was Razer. So as you might know, Razer is a big vendor, hardware vendor company that focuses on gaming peripherals. And if you want to interact with your gaming gear on a Linux environment, you will most likely, almost for sure, use the Razer software. The Razer lets you do a lot of stuff. So for example, configuring your keyboard macros, changing your RGB layouts, your mice DPI, basically everything, and even configuring this lovely RGB mag hold of Razer. Yes, that's a real thing, pretty cool. Every type of device that you see here on the screen corresponds to an additional kernel module that we have to load and to install in our system to know how to interact with it. So it expands our attack surface very, very greatly. An example of what we can do with this software could be this random Swedish flag, for example. One of the prime things that we need to understand and to know while conducting an offensive research is to know how we can communicate and transfer data between the non-privileged and the privileged part in our project, which in our case is how we can communicate and transfer data between the user space and the kernel space. In Linux, there are multiple ways to do it, which we'll go briefly over the main methods with some examples that will show us how it will basically look in an open source project. So let's start. So first of all, which is the very easiest way to implement this type of communication, is by using the read and write API interfaces, which are then accessible via the read and write syscalls. Let's have a look how it looks like. So this is a very basic template of how to implement such things. And in Linux, there's the file operation structures that you will always need to implement in order to access it. So here we need to implement our read API and write API that will point to our custom function, which here will be the device write. And then it will be exposed on a device character on the file system, on /dev, for example. Which then here, for example, if I will use the write syscall, which I will show you shortly, will actually trigger our very own device write function. This is the definition of the write syscall in Linux, and as you can see on the VFS write in the function, there is the call for our custom write function. Again, this way of implementation is very easy to do and very common. Another way to do it is by using the ioctl API interfaces, which is very common used in Windows system as well. In this method, usually each functionality is being distinguished by the command parameter which then most likely will be parsed in a big switch case in our implemented driver. Let's see. So here we configure our custom ioctl number. And again, in Linux, a lot of people think that ioctl numbers are just random numbers. But like Windows, it's not just a random number. It actually corresponds for multiple factors. So for example, if it's a write or it's get or set function, the number of the function, and the passed argument, the expected struct to our function. So here we implement our custom ioctl, and we implement the same function in the same file operation structures. Here you can see underneath the file operation structures, I implement now the unlocked ioctl API and not the read and write. Afterwards, as I mentioned, there's probably will be a big switch case parsing the command parameter. And here you can see there's a big switch case, and by the command, I know how to execute the required functionality, which then everything will be accessible via the ioctl syscall. And once again, it will run our own very ioctl API. This way, again, very common on Windows, less common on Linux, but again, that's a very common thing to do. Another very neat way to do it, which in my opinion, it's my best way to implement it, is by using the pseudo file system methodology, which you can use the procfs or sysfs, for example. Using this method, usually each functionality will be exposed on a dedicated file on this file system. So then it will be very easy to interact with your driver because, again, each functionality will be exposed on a dedicated file, and just reading or writing to custom files with shell script, for example, is very easy. So again, very easy way to write your own user space process and communicate by reading and writing to custom files to trigger your required functionality from the driver. But the downside of using this type of method is that it's a bit harder to implement. But again, I will show you a very basic way how we can do it indeed. OK, so here, let's assume that we have the my variable that I want that the user will be able to communicate with. And by communicating, it's triggering a read or write to this new variable. Afterwards, I will need to implement two custom functions. The first function will be the show function, which will be triggered every time I'm using the read syscall. So if I will do a read on the exposed file, I will get a my variable. And the second function will be the store function, that if I will pass a new variable into it, I basically will change the value of the my variable. Afterwards, I will need to get it all together. And as you might see, I'm passing the permissions that I want that the exposed file will have on the file system. So here, for example, 0660. And afterwards, I can actually create the exposed file. So this is, again, an example for the sysfs type. So as you can see, there's a call for sysfs create file, which I'm passing all the things that I've created to it. And eventually, it will just create a new file on this file system. And again, because this exposed file is triggering and responsible for only one functionality, if I know what to write and to read into it, and I know what's the expected behavior from me. And again, very cool, a very efficient way to implement your communication between the kernel space and user space. And here I wanted to show you the example of, again, I'm just doing, this is a backtrace of the user space read syscall. And again, I'm just using their normal read operation on this pseudo file system file. And as you can see, eventually there's the call for sysfs kf sec show, which will call our very own show function. So again, show function is being triggered whenever I'm doing the read syscall, and set, or the other one, for the write syscall.
So I know my colleague Tal said that his favorite way of interacting between the user and the kernel is using the sysfs and procfs. But in my opinion, the best way, in case you're in need of speed, is using memory map or mmap. So you're probably familiar that mmap can be used to have like a double mapping in user mode for a specific page to allow faster write and read. But you can also do it between the user mode and the kernel. In this case, you can do it maybe on the device file or into a shared memory between the user and the kernel, which involves that if you write data into it, then it will be always in page unless you get a page fault in case that you need to read from it. If you come from a Windows background, this is kind of similar to MDL in communication between the user and the kernel, but then you have like a map into a physical page, essentially. So let's see how to use it. The usage is quite simple. At the bottom, we see a function that we define called myMap. The first parameter is the pointer to the device tract. The second is a pointer called VMA to the virtual memory address. And we assign it to the myVM operation, which has an assignment to function in every case that we receive a page fault. For instance, we try to read from the page after we wrote from it, then the myFault function will be triggered. Again, as before, we need to implement the file operations struct, assign it to mmap the mymmap function. And the way we approach it and trigger it from the user mode is just calling call mmap on the file pointer of the device object, which is the first parameter in the mmap call. Now, the last way of communicating between the user and the kernel is quite nice. It's called netlink, which allows you to have the full socket API between the user and the kernel mode, which means it supports broadcast, unicast, multicast, and also asynchronous communication, which is kind of neat, and it's very interesting. One important thing to understand and to notice is that it doesn't use the normal TCP, UDP, IP kind of protocols. So in here, we can see that we have a constant of my netlink of the value of 30, which is not TCP or UDP. And we need to use it as identifier number when we create the socket in the kernel. So we call the netlink kernel create. The third parameter is the configuration pointer to a structure that in this case we assign to the input function a function we call myReceive. So whenever we send data between the user and the kernel, the myReceive function will be triggered. And the way to access it from the user mode is very simple. We just create a socket, again, using the same identifier as before, and we can exchange that data between the user and the kernel, and also across multiple processes in that way between the kernel and the processes themselves. So if we want to sum this part up, this entire thing was important because every mismatch of communication between the user and a kernel is a potential pitfall for bugs. So let's go back to the Razer. The first thing to see if the Razer kernel module is indeed loaded into the memory, we just run ls mode, shows us all the kernel modules, and we grep for Razer. After that, we run the lsusb command to find the path of the kernel module. The value of hexa 1532 is the vendor ID of Razer, which we need. After that, by doing that, we also need the vendor ID to understand what are the possible functions that we can access. And then, for instance, if we want to write 1 into the method metrics effect wave, it will do the following. Ooh, change the colors of this lovely mug holder. Not that impressive, but it's a thing that we can do. So let's go for the fun part, which are, of course, bugs. So the bug class that we are looking after are bad pointer dereference, originated from null pointer dereference, arbitrary pointer dereference, and all the kinds of buffer overflow and the buffer overflow. And the potential places or sinks where these things can happen are in mismatch in data copy operation, also in pointer dereference. And for those who are not familiar with the terminology that is used in vulnerability research a lot, we have a source and a sink. On the left, we have the wonderful Nikola Tesla, the inventor of the light bulb, and many other things as well. So without him, probably we won't have RGB colors. So thank you, Nikola. And on the right, we have a sink with some colors in it. I don't know why people need that. OK, let's go back to our subject. So the two approaches are go from the source to the sink or from the sink to the source, which means starting from the function you have access into the place that you can have a potential bug, or the opposite, from the place that you have the problematic operation, like strcpy or memcopy, to the target function you have access. So if we want to make it simpler, then first we examine what is the attack surface of us that is accessible. What are all the functions that we can access and call from the regular user? After that, we will see what are the arguments that we have control over and how we reach them and we're able to affect them. we see all the arithmetic operations that happen over these arguments leading to a data copy operation or pointer dereference. And then we do something we call backward tracing, which means we go back. So imagine that we have a long stick. We hold one in each end, and we try to go in the middle. And that greatly helps us to understand if we have a potential bug here or not. So in this case, we start from the data copy operation or from the pointer dereference. We see all the arguments that can lead into that have an effect on that. And eventually, we can see if the function is accessible or not. Those type of things are also very easily done by using static analysis tools or also GPT models for that matter. And let's go for a specific bug that we found in a method called Razer Chroma extended metric set custom frame 2. This method is responsible to change the keyboard colors of your keyboard, of course, between purple, blue, or whatever. And we have full control over all the parameters the function receives. The row index, the start column, and the stop column, it's pretty easy to understand. They are the keystrokes of your keyboard. The RGB data is the color that we want to change into. Can you maybe find a vulnerability here? Someone? OK. Also, we need to say that the report's argument buffer is in the size of 80 bytes. It's important to note. So the vulnerability here is pretty simple. If we see here, we can see that the unsigned character is in the size of 255 bytes. And we have the assignment of row length, which the maximum value of it can be 765 bytes. So, and we said the argument buffer is in the length of 80 bytes. So we have a run over of 765 bytes over 80 bytes buffer. So we basically have 685 run over bytes over the stack, which is a great buffer overflow vulnerability. And as we said in the beginning, that developers are a bit lazy, and sometimes they copy vulnerable code from one source to another. So here we have exactly the same bug at the function called Razer Chroma misc one row set custom frame, which is responsible to light up this mug holder. And it's completely the same vulnerability. So this mug holder can contain tea and be hot. It can contain cola and be cold. But it's most definitely vulnerable to code in this case. And also, another vulnerability, this is on the mice that you may have, completely the same vulnerability. With that, let's go to the exploitation part.
Thank you, Eran. So for exploiting this type of vulnerability in a Linux environment, so again, we got here a primitive of buffer overflow or stack overflow in the kernel. In Linux, there are multiple ways to do it, and there's plenty of information regarding it on the web, so you're more than free go look it up. I've chosen of the mod probe path technique to exploit this kind of vulnerability, and I will explain it a bit. So in Linux, when you want to execute a new binary, for example, just a generic ELF binary, obviously the kernel needs to know what type of file it requires to run. So for example, if it's, again, an ELF binary or a Python script, for example. If we want to, again, in Linux, we can just execute a new binary via the execv syscall. And if we go over the call stack, again, yay, open source Linux, we eventually will reach to the search binary handler, which again, its purpose is to do the exact thing that I've mentioned. It tries to parse the type of the binary that it wants to run. So again, if it's an ELF binary, a script. If it's a script, if it's Python or whatever else. But if we don't mention if the kernel can't parse what type of binary it wants to run, we will eventually call request module, which eventually calls the call modprobe function. As you can see, there's a very weird variable called modprobe path at the top. We will reach it soon. But eventually, this kernel function calls the call user mod helper setup, which will just spawn a new user space process with high privileges. And as I mentioned, the modprobe path is just a random string stored in the kernel. So what our exploitation technique will be, After we got the primitive of kernel write, so again, we have the buffer overflow, so we can reach eventually the primitive of kernel memory write. We can change this string. So if we change this string and we'll point it to a malicious payload, as you saw earlier here, we will call it in a high privilege user space process, user mode process. So we'll just have an execution in root permissions on the user space. So my exploit will do the following. I will create, I won't show it in the demo, but I've created a malicious payload that will just add a new user to the system with root permissions. And afterwards, I will run a mal-crafted binary. So again, the function that I've mentioned earlier won't be able to parse the type, the format of the binary, and will call our malicious payload. And eventually, we will have a new user with the root permissions on the system. Let's have a look. So as you can see, I'm running with a low privilege user, just no permission at all. Afterwards, I need to check if my vulnerable kernel module is installed in the system. And here I have the Razer accessory, which is responsible for controlling this lovely mug holder. Afterwards, I'm checking if it's connected to my device, to my system. And now I'm running the exploit of changing the string. And as you can see here, I still won't have the new user created because I need to run malformatted binary. Now I'm running the malformatted binary. And now, hopefully, I will have the new user with root permissions. Thank you. All right. So during the exploit development, we've encountered a newly added feature to the Linux kernel, which was a part of Fortify source mitigation. Essentially, Fortify source aims to detect buffer overflows in compilation time and to mitigate them in runtime. Fortify source came from glibc and got introduced into the Linux kernel in multiple steps, which introduced two modes of operations, which we will call them mode 0 and mode 1. Mode 0 aimed to detect buffer overflows over an entire struct, stack overflows over an entire struct, while mode 1 aimed to detect buffer overflows or stack overflows even on specific member of the struct. Let's have an example. Let's assume here that we have this instance struct that has 3 members underneath. arg1 in the size of 2 bytes, an array in the size of 6 bytes, and arg2 in the size of 4 bytes, followed by a memcopy operation on the R buffer. If we compile our kernel module under the Fortify source of mode 0, we can indeed still overflow our buffer of our R buffer, thus overriding or corrupting the data stored underneath the arg2 buffer variable. But if we compile our kernel module under Fortify source in mode 1, we cannot override and overflow our array buffer, thus much safer memcopy operation. First of all, Fortify source got introduced into the Linux kernel in kernel version 4.13 in 2017, when mode 0 was turned on for both strcopy and memcopy family of functions. Follow that in 2020, in kernel version 5.11, mode 1 was turned on for strcopy family of function, but still mode 0 was turned on for memcopy family of functions. Later on kernel version 5.18 in 2021, mode 1 was again turned on for both of them, but for memcopy family of function, only the compilation time mitigation. So again, if you will have, for example, a memcopy operation with a dynamic size, you will still be able to exploit it. And lastly, in kernel version 6.1 in 2022, mode 1 was turned on with runtime permission and runtime mitigation for the memcopy family of function. So now remember, if you will compile your kernel module on a Linux with a kernel version 6.1 or higher, of course, with this Fortify source mitigation enabled, you will have the buffer overflows mitigation compiled with it. Let's see how it actually looks like. So here, I hope you can see, we have our vulnerable memcopy operation from our driver. Again, I'm showing you the disassemble code because this mitigation is being inserted in compilation time. As you can see, there's no any validation on the third argument of the memcopy operation, which here will be the row length. Thus, it's the vulnerable memcopy operation. But if we look at the function with fortify source enabled, we can indeed see that there's a newly added check inserted to our binary that checks exactly to the row length variable. So here it checks if our pass row length is bigger than hexa4d, which is exactly how many bytes we have left to copy in our buffer. And if we exceed it, we will call fortify panic, which just crashes our driver safely. Again, I have to mention that this mitigation, as I know, it's only in Linux, and as I mentioned again, most of the time this mitigation isn't enabled on the machine. And if we will install third-party kernel modules, there's a good chance that it won't be installed with it. And in Windows, obviously. After finding these vulnerabilities, we reported them with a fixing PR to the open source project, which was merged and released on the very same day. This project has a couple of tens of thousands users, so it's kind of important. Multiple CVEs were assigned to the vulnerabilities we found, and there's a couple of more under disclosure. And there's a very nice blog post published on CyberArk Lab's site, going much deeper into the vulnerabilities and to the fortify source mitigation. So you're more than feel free to check it out. What's next? Maybe we've mentioned Windows, maybe. We've mentioned a lot of Linux. And maybe next time we'll talk about a more Apple-ish operating system. We haven't decided yet. Some takeaways. For developers, of course, you need to make sure that you're running and you're developing with all the newly mitigation enabled and all the cool things that you can make your application more secure. So again, in our case, make sure that you're developing your application in the newest machine with the most mitigation enabled. And maybe if you want to integrate your CI/CD some static analysis and even consider fuzzing, as we mentioned, maybe dump fuzzing. Again, it's very easy to write and very efficient from my experience. Some advices or not advices for attackers. Again, everything that we need to know is how we can reach to our vulnerable devices. So we need to make sure that we have permission to do so. So if you're a defender or developer, make sure they don't have permission to do the things. And static analysis for the developers as well. And for the defenders, make sure, again, maybe the developers don't know the newly added mitigation and all the security stuff. So make sure you tell them about the mitigation and make sure your own product is well run and well kept. And some advanced thing, you can monitor a system for malicious activity. So for example, malicious syscalls that talks to your exposed devices of your kernel modules. And basically it. And stay safe. That's it. Thank you very much.